Hi, welcome to Mean 221. We are just going to talk today about an example for how to compute torque and moment in 3D. As promised, my image will not cover, I hope, much of the text. And for those of you who are willing to stick it out to the end, okay, so what are we trying to learn in this session? Item number 1, we are going to learn how to compute torque or moment in 3D. And item number 2, out of the torque or moment, you will get a vector. And then you want to find out how much bending and twisting is involved. It should say twisting and not twisting. So let's fix that. Remember that we talked about the importance of bending and twisting. These are the two primary modes of failure for most things. So that's why we are interested in that. Okay. So this is a fairly straightforward deal. So just to get your importance of moment or torque, I mean, on the engineering side, I've shown you like a sideways drilling or a lateral drilling well. And what happens is that you have to rotate something. That's how wells, oil wells are drilled. And when you bend something or twist something or, do one of these things, you are always worried about whether the joints will fail. Second example is when you're doing arm wrestling, for example. You can see those two large people trying to do arm wrestling. Or if you're doing golf, or if you're a baseball or softball thrower, and then you have to worry about how do you get spin onto the ball. I myself am a cricket fan, so there's a lot of stuff about how do you get the ball to swing or how do you get the ball to spin and all that. So exerting and controlling the torque and bending moment are key to both sports and engineering. And from the point of view of sports, this is very, very important from the point of view of sports injuries. So I want you to understand that yes, you can do all this stuff, but if you know how much torsion or torque you're applying to various joints in your body and how much bending you're doing, you can get an idea of how badly damaged things are. And that's one of the reasons why if you're a baseball pitcher or something like that, or if you're a cricket bowler, things hurt pretty badly, okay, after you finished your game. Okay, very good. So enough of the background. So let's get to the problem. So I have a very simple example of calculating the moment of a force on a bent pipe or an elbow. So one of the challenges for you is to imagine this in 3D. Can you see the X, Y and Z axis? So the Z axis is pointing up, the Y axis is going that way, and the X axis is going towards you, right? So those are the three things. And what is happening is that I have a bent pipe. This is along the X axis. This is along the Y axis, up to this point, and from here to here is along the X axis. This is along the Y, this is along the Y, this is Z axis, this is X axis, and you can see I've drawn the shadow so that you can kind of visualize this thing. And then at the tip there's some force, and I've given you the force vector 40, 20, minus 10 newtons. The question is, what is the moment at point O? And how much bending is involved on the bar OA, and how much twisting is involved in the bar OA. So let's see what we need to do. So there's the point O, there's the point A, and its coordinates are 0, 3, 0. The point B is coordinates 2, 3, 0. You know how to do that, right? Point C is coordinates 2, 5, 0. Just in case you don't know, if you want to find the coordinate, you just ask how much along the X axis do I walk, how much along the Y axis do I walk, and how much along the Z axis do I walk. So to get to point B, I have to start at point O and take 3 steps in the Y direction and 2 steps in the X direction. So it's 2, 3, 0. Okay, you know what I mean, right? So point D and then point E. Okay, so I want you to understand that these kinds of things are quite straightforward and simple to do. Okay, so let's see. We found all the points. Next thing to do is to say, if I want to find the moment vector at this point, what I do is I take my vector from O to E, which is where the force is acting. Moment arm vector is this. And this is my force vector. and what we need to do is do a cross product. So which is my moment arm vector is O to E, which is 5 minus 4 crossed with the force vector, and the units are Newton meters. Why? This is in meters and that's Newton, so the resulting unit is Newton meter. So in the FPS system it will be foot pound, in the SI system it will be Newton meters, and in the engineering system many times people will use kilonewton millimeter or Newton millimeter or something like that, depends upon the situation. Okay, so you got to do this cross product. One way to do it, just do it. Another way, what I usually do is, because I like to do this, is to say mx equals yfz minus zfy, which turns out to be, let's see, y is 5 times fz is minus 10 minus z is minus 4 times fy is 20, which turns out to be equal to 30 Newton meters. My turns out to be, this is y goes to z, z goes to x, x goes to y, so zfx minus xfz, and again you can calculate this pretty easily. Z is minus 4, fx is 40 minus xfz, x is 5, fz is minus 10, so that will turn out to be minus 110 Newton meters, and then mz equals xfy minus yfx, which turns out to be, if you do the same thing, it will turn out to be a minus 100 Newton meters. So my vector looks like 30 minus 110 minus 100 Newton meters. It's not complex, just R cross F, nothing to it. Okay, now comes the key question. How much of this vector is twisting and how much of it is bending? Twisting equals moment along the line, bending equals moment perpendicular to line. We did this exact same thing with forces, so we're going to do this. In our case, the line is along the y-axis, so this is the y-axis, so I have to look at how much is the moment along the y-axis. That's twisting. Now notice that the bending is the remaining, but we have to find the magnitude. So what will happen is, bending will be total square root of total squared minus twisting squared. So this is easy. This is minus 100 since the line is along the y-axis. So this will be, turns out to be square root of what is that? Let's see, 30 squared plus 100 squared plus 110 squared minus, so this is 110 minus 110 squared. So it's square root of 30 squared plus 100 squared. That's the bending. You got the idea, right? So I calculated the moment vector. I found the twisting by taking moment dot unit vector in the direction. In our particular case, the unit vector was very easy. It was just in the y direction. So unit vector EY is just the j component. So I didn't even have to do line vector over line length. You know what I mean? So this was actually pretty easy. Okay, now what I want to show you is that the same force will have different effects and different moments at different points. So I computed from here. Now I'm going to compute from here. So what's the moment? What's the torque on this bar? Okay, at this point. So each point along the bar will have a different amount of torque and a different amount of bending moment. So I want you to understand that. Okay, so if I want to find the moment at B, I have to look at this vector. So from B to E, which is E minus B times F. E minus B turns out to be, let's see, 3, 2, minus 4 cross f turns out to be 40, 20, minus 10. You can do the cross product yourself. You can do it whichever way you want. You can do it the way I did it. You don't have to do it, but you can do it the way I did it. If you, whatever it is, you should get, this turns out to be, this is meters, that's newtons. So this will give me 60 minus 130 minus 20 Newton meters. That's my moment vector. This is moment vector at B. Now if you want to find out torque along AB equals moment vector at B dotted with EAB, which is the unit vector along AB. That's the direction vector along AB. That turns out to be moment vector along B dotted with EAB is the x direction. So this is IE. So if you do the dot product, that's pretty easy. That's 60 Newton meters. What about the bending moment along AB? It will be square root of MB magnitude squared minus 60 squared, which will turn out to be square root of 130 squared plus 20 squared Newton meter. Got the idea, right? So typically speaking, you want to calculate the torque first, that is moment along AB first. So steps are easy. Find the moment arm vector, cross it with the force vector, you will get the moment vector. Then find the torque along the line and then do Pythagoras theorem. Okay, that's it. Very good. So, hey, no comment is needed. Enjoy the cartoon. Thank you. Bye.